Here are solutions to test number 1 for ECE 376. This test looks at binary inputs, binary outputs, and assembler programming on a PIC 18F4620 microcontroller. The first problem looks at a binary input. Suppose I have a light sensor where the resistance changes with light level by this equation. Come up with a circuit that outputs 5 volts when it's less than 10 lumens, 0 volts when more than 15 lumens. So this is kind of what it looks like. I turn on right here at 10 lumens. I turn off at 15 lumens. Well, to do that, first you calculate what is the resistance at 10 and 15 lumens. So you get 2511 ohms and 1969. Next, I want to convert that to a voltage. So pick your favorite voltage divider. Here's my resistor. I chose something in the middle. What did I choose? Oh, choose your birth date. So for me, that'd be 1414 ohms. That's if you're born on Mother's Day. ohms. Then do some voltage division. By voltage division, the voltage right here, call it Vx, is your R over R plus 14. So it turns on at 3.11 volts and turns off at 2.82 volts. So this is kind of drawn backwards. Voltage is what the circuit cares about. The on voltage is more than the off voltage, so oftentimes I'll actually draw it like this. I turn on at 3.11 volts, turns off at 2.82 volts. The circuit really just cares about voltage. So since the on voltage is more than the off voltage, I connect to the plus input. The on voltage is what I make the offset. And the gain is the slope. The output changes by 5 volts. As the input changes by this amount, gain is 17. Pick this to be 17 to 1. So there's a Schmidt trigger that'll turn on at 10 lumens, turn off at 15 lumens. Problem 2. This looks at a binary output. Suppose I want to turn on and off a yellow LED at, for me, 14 milliamps. Come up with a circuit so a PIC processor can do that. Well, off is easy. When the output is 0 volts, IB is 0, IC is beta IB, also 0, so 0 is off. That part's easy. The on voltage is where you got to work. When this is 5 volts, I want that to be 14 milliamps. First, let's find RC. RC is the voltage across the resistor. That's my 10 volt source, minus 2.4 volts across the LED, minus 0.36 volts across the transistor at 14 milliamps, makes this 5.12 ohms. For the base resistor, I can pick AB or IB to be almost anything I want. Subject, it's got to be less than 25 milliamps, because that's all the PIC can do. And I have to saturate. To saturate, IC is beta IB, so IB has to be at least IC over beta, at least 7 milliamps. Pick a number between 7 and 25. I chose 10 milliamps, so if IB is 10 milliamps, the resistance is then 5 volts on the left. This is a diode. The voltage drop across the silicon diode is about 0.7 volts. 5 minus 0.7 is 4.3 volts. 4.3 volts at 10 milliamps is 430 ohms. So this works. There's actually a wide range. As long as IB is between 7 and 25 milliamps, it'll work. Problem 3. Suppose I have this case. W starts out at 5, port B is 35, port C is 14. What happens after each instruction? Well, the first one is a read, copy port C to W. So 14 goes to W. This says move port B to port C. 35 goes to port C. And now move W to port B. That's the right command. W goes here. So what I just did is I swapped. Port B and port C are now swapped. This is 14, this is 35. Next, move the number 7 to W. Now do exclusive OR. I'll take B, exclusive OR it with W. Okay, look what just happened. Fixing that, I've got at this point, W is 7, port B is 14. Take 7, exclusive OR with 14. And you do that bit by bit. So the number 7 is 0, 1, 1, 1. 14 is 8, 4, 2, 0. There's 14. Exclusive OR. Exclusive OR is if they have an odd number of ones, the answer is 1. So you get 1, 0, 0, 1. That's binary 9. The answer is 9. So 7 exclusive OR 14 is 9. It's a bitwise operation. Toggle bit 0 of port C. So 35 is 32 and 3. So it's 35 in binary. Toggle this bit gives you 1, 0, 0, 1, 0. That is 34. And finally negate port B, put the result in W. Minus 9 is minus 9. And if you don't like negative numbers, this is 2's complement, so you can always add or subtract 256. This is also the same thing as plus 247. Either answer is correct. That's problem 3. Problem 4 looks at how long this code takes to execute, where this is your birth month, say 5, this is your birth date, if you're born on Mother's Day, 5/14. To do that, you count. I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 instructions in this loop, plus 1 for go-to. That takes 12 clocks. This executes A times B times C times. In red, I've got 1, 2, 3, 4, 5, 6, 7, 8, plus 1 for go-to. 9 instructions in that loop. That's executed A times B times. In green, I've got 4, 5, 6, plus 1 for go-to, 7. Executed A times, and in black I've got 1, 2, 3, 4, plus 1 for go-to, 5. So the total number of clocks is 12 ABC plus 9AB plus 7A plus 5. Plug in A is 5, B is 14, C is 177, and I get 149, 350 clocks. Next, let's modify it so that the total is 22 million. So one way to do that is I'll max it out, make A 255, B 255, solve for C. And, well, C 255, it'll be too large. So a couple ways. This is kind of like cracking walnuts with a freight train. A is 255, B is 255, C is 255, N is 12 times A times B times C, plus 9 times A times B, plus 7 times A, plus 5. I want that to be 22 million. Too big, so let's just scale it. C is 22 million divided by N. Scale C. So C should be 28. And let's round up. So what did I do? And CAC is 28. 29. If I try that, recalculate N, it's close, but still too high. So let's scale up B. B is 22 million divided by N times B. So make B 241. 242 should be closer. B is 242. Now let's try it. And there, that's pretty close. I could maybe try to tune A. A is 22 million over N times A to, well, that's about the best I can do with this approach. So net result is here's A, B, and C. That'll get me close. 22,032,000 I'm up by 32,000. Other combinations also work. Problem 5. Convert the following flowchart to assembly. This goes block by block. So the first one, if I want to make port B input, C and D output, that's move FF to tris B, clear tris C and D. To clear port C and D, I just clear port C and D. Those are assembler commands. Check the 8-bit value of port B. If the 8 bits are all 0, exit. Otherwise, if it's not 0, keep looping. So this is actually compare skip if equal. I'll move 0 to W, compare W to port B. If it's equal to 0, I skip out. Otherwise, I go back to loop 2. So that's this loop of code. Next, keep on looping while it is 0. Kind of same approach. I'll move 0 to W, compare to port B. If it's equal to 0, I'll skip and go back to loop 3. If it's not equal to 0, I don't skip and go to loop 4. Or label 4. Label 4 is port B bit 0 equal to 1. This is a bit test. That's a bit test. Port B, comma 0. If it's clear, I skip. Otherwise, I don't skip. If I don't skip, I'll increment port C, put the result in port C. I'll then check bit 7 of port B. Bit test, skip if set, port B, comma 7. If it is a 1, I go down here. Otherwise, I go back. So 1, I skip. Otherwise, go back to label 2. Is port C equal to 42? Again, this is a 8-bit test. Move 42 to W. Check, is port C equal to 42? Equal to W. If it is, I skip. I'll write FF to port D. Some code right here. Wait 2.2 seconds, then return. And that is test number 1.